Hi, everyone. I'm Jacob Schwartz. I'm a staff research physicist at the Princeton Plasma Physics Lab, which is a Department of Energy funded national lab managed by Princeton University. I should say, as like standard disclaimer, the content in this talk is not necessarily the position of PPL or DOE or anything like that. I should also say, so I'll be talking about materials for fusion energy. I'm not actually a materials scientist, although my PhD work was like materials adjacent to using plasma physics and gas physics to protect the materials. But I'm interested to meet those people in the audience who are interested in material science and atomic precision manufacturing and technology, and let's chat about this. Cool. So let me give you the outline of the talk. First, I'll be talking about the development of controlled flight as an analogy for the development of fusion. Then I'll talk about the drivers of fusion. Why does the reaction make the materials problem difficult? I'll talk about the specific requirements that the outputs of the reaction impose on materials and why it's challenging. Some possible solutions, and then finally, why even like testing and maturing fusion materials is challenging. So I think the development of flight may be instructive for the development of fusion. In the early days of aerospace research, there were a lot of different ideas about how to fly. Eventually, in 1903, the Wright brothers demonstrated powered, manned, controlled, heavier than air flight, and that became the dominant paradigm. But I didn't fly here on a plane made of sticks and cloth. In order to enable mass commercialization of air travel, we needed new materials like anodized aluminum. Actually, this is regular aluminum, but aluminum invented for air travel. We needed things like single crystal nickel alloy turbine blades to enable jet engines to be bigger, burn hotter, more efficient, fly further. Similarly, with fusion, we've just now are at the point of demonstrating the scientific feasibility of get more energy out of the reaction than you put in. But it's going to require new materials to be able to compete economically against everyone else producing electrons, putting power on the grid. So Adam already talked about some of the physics of the fusion reaction. I'll just review that very briefly from my own perspective. Oops. So these two isotopes of hydrogen, deuterium and tritium, they produce this fast alpha particle, this helium nucleus, that goes back into the reaction, keeps everything hot. And this neutron, which goes into the wall of the machine, I think of it as sort of a billiard ball process. It expends its energy, heating up the wall, and that's the thing that you drive fluid through in order to produce energy, like a steam turbine, something similar to that. So in a very generic sense, a fusion reactor, you can think of, there's this pink plasma thing in the middle. It's surrounded by these, first surrounded by vacuum and white, and then by layers of material. So there's typically a first wall, only a couple of millimeters thick, made of something like tungsten. And then about a meter thick of blanket materials, which contains the lithium that you need to breed tritium and so on, other structural things. So the plasma itself imposes some loads on the wall. So the plasma is very hot. It's radiating X-rays. The plasma itself eventually diffuses out of the confined region, and ions, electrons, and impurities hit the wall materials and can affect them. So I should also talk about the difference between neutrons in fission and in fusion. So regular nuclear plants famously work using a neutron chain reaction where uranium goes to one neutron, goes to another uranium nucleus. But in a fission plant, the neutrons only carry about 1% of the power, and they typically have energies of 1 or 2 MeV, whereas fusion, the neutrons contain 80% of the power, and they're each about 10 times higher energy. So this imposes a lot of requirements on typical materials. I'm going to talk here about something like the first wall, solid materials, especially tungsten. I'm not going to go over all of these. I'll just let you read them for a moment. So just as a sample, the first wall, it needs to pass through about 20% of the power of the reaction. It needs to carry megawatts per meter squared. And it needs to operate at high temperatures. And if you aren't careful, it can do things like crack under thermal fatigue. So this is a picture from somebody's kitchen, actually, of like a gas burner that was heated up and then cooled down many times until it started to crack. With something like tungsten, when it's exposed to plasma, sometimes it just erodes, but in certain conditions, it can actually develop this fuzz that grows on it as it's eroding. And then the fuzz can like flake off, get into the bottom of the machine, cause dust and troubles. Probably the biggest problem, though, is neutron damage. So I often think of neutrons as acting like billiard balls. They pass through a lot of solid material because they only interact with the nuclei. But when they do hit an atom in the nucleus, it's like a cue ball hitting a break. And so you can see in the simulations, one atom that gets hit eventually causes this sort of zone of liquidization, a zone of local melting inside of a crystal structure of a material on a picosecond timescale. Now, most of the atoms eventually come back into place. That's very remarkable. But in the lower right, you can see there's 4 or 5 atoms that are not in the right place. They're called defects or interstitial atoms. And over time, these will weaken the structure of materials. Now, we need to achieve economic fusion materials that can survive multiple, like tens of displacements per atom. So every atom needs to be knocked out of place and come back multiple times. And that's difficult. So ultimately, I think the economic success of DT fusion is going to depend on whether we can master controlling materials that are held together by 20 eV kind of scale chemical bonds against the power of the 14 MeV neutron. But we have some cleverness. So there's a lot of different ways to modify tungsten. You can do things like tungsten heavy alloys, high entropy alloys, tungsten fiber, tungsten composites, particle dispersion, strengthened alloys that all modify the material properties to make it more ductile under high neutron fluences and improve properties and like oxidation. There's also things like silicon carbides, ultra high temperature ceramics that actually melt at even higher temperatures than tungsten, or even liquid metal plasma facing components, which is a particular area of interest of mine. Liquid metals are nice because you can't damage the crystalline structure of a liquid because there ain't any. Um, in general, it's difficult to test fusion materials because we don't have a fusion reactor to create the 14 MeV neutrons. Uh, the default path for this is this place called the International Fusion Materials Radiation Facility that's being put online in Spain, but they're not going to start operating until 2034. They can only test very small samples, and it's still going to take years to test a single sample of material. Meanwhile, to make a fusion supply chain, we need to not just have the materials, but the engineering, fabrication, bonding, welding, supply chain standards, and so on. So we might think about whether we can use AI, uh, like even quantum computing to simulate materials and how they operate in silico. And this is what I'd be interested to chat about. So thanks so much.